Let's get into cropping and resizing because those are two basic operations that we often do using image editing software. So let's say that my image, this black box, is 1200 pixels wide and 700 pixels tall. Let's say the portion of the image that I want to crop to is this yellow box. What I have to give Pillow in order to crop to that size is the location of this corner and the location of this corner at the bottom. So I have to give it the coordinates in pixels, the width and the height of this, and the width and the height of this. So I'm going to say it's over 300 and down 150. And then for this one, I'm going to say it's over 1,000 because 1,200 is all the way over. So about 1,000 and 600 down out of 700. And then what it returns is a pillow image object that is this portion of the image. The original does not get altered. It just returns that part of it. So if I want to crop that image and then show it, okay, there's a portion of that image. Now, that's not a great crop, so let's take a look at the image and find something in there that we actually want to keep. So let's try and get just this building here. So I want, that's about 255 wide by 580. So we'll say 250 by 600, right? 250 by 600. And so that upper corner is going to be 125 by 350. 125 by 350. And then if I want to find the bottom corner, I can just do this. 385 by 933. 385 by 933. Obviously, this is cheating to do it this way. But if I show that now, there's my building that I cropped. Okay, so pretty close. And so crop works like that. And I want to draw your attention to the fact that it has two sets of parentheses. Anybody want to guess why it has two sets of parentheses? Confusing, right? I often forget the second set of parentheses. Crop takes only one argument. And it takes an argument that is a tuple that has four things in it. So the innermost parentheses are representing a tuple that has four numbers. So you give it one tuple with four numbers in it, and they are the x-coordinate and y-coordinate of the upper left corner and the x-coordinate and y-coordinate of the bottom right corner of that object, as you can see right here. So that is how you crop. And remember, cropping does not damage or change the original image. It just returns a new image that's cropped, that represents the cropped space. Resizing is a little bit simpler, but you'll notice that it does still take a tuple. The resize only takes two numbers, and all it wants is the new height and the new width of the image. Now, the original image and the small image, or the resized image, presumably you want them to have the same dimensions, right? If you resize a picture of your mom and you don't resize them the same amount proportionally, then you could make your mom look like she weighs 300 pounds extra because the picture is too stretched out. Surely you've seen those online. So when we resize something, generally speaking, you don't have to do this, but generally speaking, you want to use the same factor for the height and the width so that the image is proportional. So in this case, what I'm doing is I'm taking the image width and floor dividing it by 4, which gives me an integer, not a float, because you can't have a float that represents a number of pixels. I can't have 3.5 pixels in an image because a pixel is the smallest possible unit. You can't divide them. So I have to have an even number of, a whole number of pixels. Image width, floor divided by 4. Image height, floor divided by 4. So I'm taking whatever the original image is and just resizing it down. So if I want to do that with this image, let's go with 4 for now. So when I run that, there's my resized image. Now it doesn't look like it's exactly proportional to this image, or 1/4 height and 1/4 width, because like I said, the full size image is sometimes not displayed at 100%. All right. Now I want to take this opportunity to point something out to you. Notice these up here. These are the file name that Preview thinks it's opening. Now I opened a JPEG, and right now it says a random set of characters .png. So when I open, or when I show a pillow image, no matter what it started out as, it's always going to be a temporary PNG file. So when I close these, they don't exist anywhere on my computer anymore. So another interesting thing about this is what's happening when I'm resizing this. So this time I did it at 1/10 height, 1/10 width. Think about what's happening, right? The new image size, print image 2.size. So the new image size is 192 and 127. The previous image size was about 10 times that, right? So 1920 by 1273. So I went from almost 2,000 pixels to just under 200 pixels wide. Where did all the pixels go? Well, that's the interesting thing. When I go from a big picture to a small picture, I throw the pixels away. They're gone. So when I zoom in on this little tiny image, if I make the window the same size, and then we zoom all the way in here, you can see there's not as much image data there. It's not as sharp because there aren't as many pixels. Here's the problem that people often don't realize, is that once I have this size, I can't turn it back into this because the data is gone. The data is gone. Now, I can sort of guess at this. If I say, let's copy this, and I'm going to take that image 2, and I'm going to make an image 3, and I'm going to, instead of making it 10 times smaller height and width, I'm going to make it 10 times bigger. So I'm going to just restore it back to its original size in pixels. And I'm going to start out with the small one. And then I'm going to say, let's show that image. So I'm going to show the original one, And then I'm going to show the tiny one, and then I'm going to show the bigger one. Actually, the tiny one is going to get shown last because the show is way down there, but let's just run it. It's working. You can see it's still running. Takes a minute. Okay. So there are the three images. So we have the original, and we have the tiny one, and we have the tiny one after we expand it back. So it doesn't look as bad. It doesn't look as bad as this one, right? If I make it, let's make this one big so we can see those pixels. Okay, so it doesn't look as bad as that. But you can also see, if you look closely, like on this roof line where there's high contrast, you can see it's still kind of jagged. That's not a jagged roof, guys. That's a smooth roof. But it's jagged because what's happening is we're taking a very pixelated picture and we're saying how we're adding pixels back in. Where do the pixels come from when we add them back in? They don't come from the original. It's guessing, it's interpolation. So it says we need to add, for this pixel, we need to add 9 more pixels based on that pixel. What's it going to do? It's going to look around. It's going to look at this pixel next to it and this side and this side and this side. And it's going to say, how do we add 9 pixels for this one pixel? It's a mathematical formula. There are more advanced formulas that do a little bit better job. But I'm here to tell you, I'm here to shatter the illusion of years and years of watching crime shows. CSI has lied to you. Every time they have a security cam photo of somebody all the way down the block breaking into a building, and it looks like a blurry mess. And what do they say? What does the guy in charge say? Yes, let's enhance that. And then what happens? It goes from this garbage to like seeing the stubble on the guy's face, right? And it's like, wow, that technology is amazing. It's a lie. It doesn't exist. Because once you don't have the information, it's guessing. What can we do that's pretty good? We can use AI to say, oh, I think that's a face. What might that face look like? But AI is just using other pictures of other faces that it's been trained on to say, that kind of looks like a nose. Let's make that look like a nose. We're drawing. We're still guessing. It's not real. There is no enhance that, guys. So I'm sorry to shatter that for you, but every time you watch a crime show where they do that now, you're going to go, I remember. That's a lie. So sorry to ruin it for you, but I'm going to ruin it even a little bit more. The AI that we're using now for that stuff, guess what it does a really good job at reconstructing? There's a certain kind of face that our AI software does better than all other kinds of faces. You want to take a guess at it? White dudes. Why? Why are white guys more recognizable, easier to reconstruct, easy? Why is everything leaning that way? Why do you think that is? Because the AI software was made predominantly by white guys. It's women, people of color, anybody with really dark skin. AI sucks at it because we don't have enough people who don't look like me programming the software. And that's a huge danger in our world of not having diversity in STEM. So just keep that in mind. Like by going into STEM and not being a white guy, you could do the world a huge favor. So enhance that as a lie. And once we lose information, well, that's a lot of copies of that. Once we lose information, we can't get it back. That's the thing you want to take away from this. So if you resize something down, the information is gone. The moral of the story, the big takeaway here is when you have an original picture, the quality of your picture will never get better than the original that you shoot. Always make backups. always keep a copy of it somewhere safe on Google Photos or whatever. Just keep a copy of everything somewhere safe. Because everything you do, whether it's an Instagram filter, even if the filter makes it look better or more presentable, the quality of that image, every time you touch it, every time you process it, every time you put it through a mathematical formula, gets a little bit worse. So always protect your backups. And by the way, when we get to the saving part, I'll remind you this again. Never save an edited image with the same file name as the original, ever, because you'll overwrite it. So that is my little soapbox for the day.